So let's get on to the topic of today. And this is 0201, 01005, and obviously the next generation of smaller components. Now, back in 2002, I produced a report with a number of other engineers from the Smart Group. And this report is still freely available if you would like a copy of it. And we did this to raise money for charity in the UK, and also it raised charity money in the US for different organizations. And this was about 40 or 50 pages specifically on processing, components, design, and some of the results of our own trials. So that was back in 2002 when 0201 components were going to be provided to the industry as an alternative for 0402. In 2004, I produced the first two training bits of material which are available from the IPC. And this was an interactive CD-ROM as well as a photo guide. The idea with a photo guide is people could put together their own training material through photographs of all aspects of the technology. Over the last few years, other publications have become available within the industry. A book was written by a couple of engineers from Assembleon, and two sections of this pick up on the processing of 0201 and 01005, looking not only at the placement but also of the printing and soldering side. Siemens have also done a fair bit of work on the use of this component technology, and they put together a publication a couple of years back, again specifically on 01005. And if you were lucky enough to be invited to special workshops that they ran in Germany as part of Productronica, they've also done a lot of work on the newer generation, the next smallest component, which we'll also talk about during this session this morning. So again, there's a lot of material within the industry. All you need to do is search it out. So let's just talk about the components. Now, again, there's sometimes a little bit of confusion. Different engineers use different terminology, and that's sort of probably because either you're a young engineer or an old engineer. Me being an older engineer, I tend to use imperial measurements rather than metric, because that's how I sort of started in the industry. And you also tend to use that terminology if you're from the US. So a US engineer would talk about mils, which is in fact the same as imperial measurement, parts of an inch, whereas mils sometimes is confused with the metric. So what I've done here is just shown you the components, the imperial code or metric code for the chip components, and I guess that you can look at the dimensions and figure it out for yourself. Now, up until I guess, fairly recently, and still with a lot of companies, the 0402 is the most common component which is used as a passive part, both resistors and capacitors. And then as companies needed more and more packing density, they've gone on to smaller chip components. And so we've seen the use of 0201, not extensively, I would say, on board technology. We've seen it in modules for mobile phones, or modules in earpieces, for medical applications, etc. So we haven't seen it extensively used. So 0402 really was the sort of stop point for most companies. And now 0201 is sort of the next generation, but there are two sizes below that, and we'll explore some of the issues associated with both of those during this webinar this morning. So if we just look at an example, and I don't think this is a great example because when we're using very small passive components, we should be able to get a much bigger or better density than we've actually been demonstrated here. But this is just an example. So what you can see here is a range of capacitors and one resistor mounted in position, and you can see the general dimensions for this particular part. and you can see there is a 10th hour 250 micron separation between the capacitors in this particular example. So that's not great, or it's not very fine packing density, but it's an example of 0201 being used on a real printed circuit board in an application for electronic assembly. So just as another example of the small size of these components, if you didn't or weren't aware of it, here we see the general progression of components down from 1206, 0805, 0402, and then down to the small parts we're talking about generally in the industry. And if we look at a part, we can actually take it and, just like they demonstrate, put it in the eye of a needle. So that is an 01005 component in that position right now in the eye of the needle. But we will be mentioning the next generation down as well during this workshop. So what are the challenges? Well, printing is certainly one. Now what I'm showing you here is just two video demonstrations which you can see online, where we're printing directly onto glass. Now I did this as an experiment a few years back just to demonstrate printing of 0201 chip components directly onto glass rather than onto a PCB. It allowed us to video what was going on as part of the printing process. This technique has also been used by NPL on our MPM printer in our laboratories, again to show paste printing and paste release from stencils. MPM as a company, and I feel sure that DEC has done exactly the same thing to learn about how material enters and exits from the stencil aperture. So the actual aperture we're printing is obviously dependent on the particle size of the paste, which again we'll mention a little bit later on in a little bit more detail, but it's also the quality of the stencil. Now a lot of people talk about the use of laser cut, electroform, and some of the other enabling technologies to improve print quality. But it all starts off with getting the aperture right. There is now guidelines provided by IPC on the type and size of apertures for particular components and particular technologies. And of course, stencil manufacturers give you guidelines. But one of the things we perhaps don't look at in detail is the quality of the stencil we actually get. And the side wall of the stencil is particularly critical. If we're going to be using laser cut stencils, then the material actually used to produce the stencil is important, because whatever method you're using to produce a stencil, the actual material can be quite important to give you a nice surface, unless then you do some other treatment of the stencil aperture. Of course, you've heard of nanotechnology to help release of materials, but fundamentally, if you've got a rough surface because of the material you've used to make the stencil or the process you've used, you're not going to improve that significantly. The key thing is starting from basics, getting the aperture size right, and then obviously producing a good quality stencil. Now, unfortunately, if we want to go to smaller particle size, this impacts generally on cost. So over the last, I guess, probably 10 years, type 3 powders have been used. And type 4 powders, and this is the particle size of the individual parts of the solder paste we're talking about. Now, IPC defines type 3 and type 4 and type 5, etc. By the range of particle size within the paste. Now, type 4 used to be a lot more expensive than type 3. For most companies producing medium volume to high volume, the cost differential is not significant really today. So using a type 4 paste powder for most applications is perfectly sensible and reasonable, and certainly the print quality you should be able to achieve, even on some of these small parts, can be achieved with a type 4 paste. Some manufacturers are starting to use type 5, indicating they get better paste release and better consistent quality. That's fine, but you've also got to be mindful of the fact of the cost that you might be paying. So if you can print and get successful quality with type 4, that's a sensible thing to actually do. The other thing is moving on to a type 5 material, you've got a greater surface area of the metal content, which in an air environment might lead to poor reflow, or might lead to what people refer to as graping in the trade. So incomplete coalescence of individual particles within the solder joint. Again, we'll look at a couple of examples of that a little later on. Now, if we look at placement, now I've put in 3 video clips. These are high-speed video clips which were produced by individual companies when they were developing their technology. And what you're looking at here is a part being picked out of tape by the head, of course in slow motion, but the part is actually being lifted out of the tape by the vacuum pickup tool. So it's just a nice example of that. So that's an 0201 part. The next example is an 01005 being picked, and you can see a slight difference in the nozzle being used, and this particular example is a capacitor being picked up as opposed to a resistor you saw in the previous example. And this just gives you a feel for what's actually happening at something like 1,000,000 times a second. I exaggerate, obviously, but you've all seen the speed of machines working today. And then the third example, again high speed, where you can see the individual components being placed, in this particular case onto a demonstration board, by the pickup tool. Okay, and finally, after pickup and placement, we reflow. So what you're looking at here is 2 video clips showing the reflow of solder paste on a board for 01005 chip components. So just running them again so you can see the reflow take place. First of all, on the left of the resistors, and then secondly on the right with the capacitors. Now, these designs on this particular test board are sort of maximum pad-to-pad separation on the examples. And over time, what we've done is looked at the design rules and improved them. And I tend to be an old school designer. I don't copy what it says in the booklet from the supplier. I tend to like to measure the parts myself and then create the design rules from that. It's a personal thing. It's just the way I am. And slowly you get the best and most optimum performance for the design for your particular PCB. So that's just a couple of examples of reflow, and that's successful reflow, as you can see, of a lead-free product at 240 degrees Celsius for those 2 terminations. Now, again, what's happening in the industry as a whole? Well, this is just a graph taken from Urata, and they've had or used this graph for quite a few years now, and this is sort of the latest version of the graph, just showing the trends. So component percentage ratio against years. So you can see how certain components are growing in popularity, some obviously reducing in popularity. But the interesting thing is you can see that the 0402, although theoretically peaked in 2006, there's still over 30% of these parts being used. It is suggested by 2006 that 0201 will exceed the use of 0402. But the other parts we're talking about at this moment in time is still sort of really growing. So we're only looking at 10% usage of 01005, and the next generation down, the smaller packages, again, only just getting off the bottom of the graph in 2006. So it's useful to understand trends because that obviously impacts on component availability and also the cost of these particular components. But as I always say in design for manufacture reviews, never use a technology unless you need to do it. However, there is a benefit sometimes of taking a product and introducing a component because that's a learning curve for you. And when I say a learning curve, you can practice on a real product So you're seeing yield against producibility. You can obviously use test boards. So sometimes perhaps it is worth using technology when it's not necessary on a particular product. Again, it just depends on who you are in the industry, whether you're a user or a contract manufacturer. A contract manufacturer would normally use test boards to assess the performance of his process and product as opposed to an active product. Now, with the small components, you have to ask the question, do we really need to use them? Because also, over the last few years, there's been a lot of interest in componentry built into the printed circuit board. So integrating passive technology or passive component technology into boards. And this has been used and is in fact used by certain manufacturers, where they're actually placing the components into partly built substrates. So this can happen. Or we can use conductive materials, conductive inks, etc. I've done some experiments on this, but not necessarily very successful experiments. Now, if you're interested, there is a book, it was written, and I believe it's the only one that exists on the integration of passive component technology into substrates. This was written by Richard Ulrich, an American engineer working out of one of the US universities. There's also an IPC standard on the use of embedded components and some design guidelines in that area. So again, that's something you might like to consider reviewing before you introduce a technology to your company. Now, going back a couple of years, and I apologize that some of the data here I'm presenting is a little old, but the problem is within the industry, it's not necessarily always bang up to date what is available. And obviously, if somebody's done some work, there's no point in repeating it unless there's a value to it. So this is part of a study that was done by a US organization, DFR Solutions, and they showed that the smaller component technology, the O2, 01, etc., was mainly being used in FR4 modules. And when we talk about a module, we're talking about something that you would then introduce into another product. So a classic example of that might be some of the small modules that are actually included in smartphones. So if you're an older engineer, you might think of it as a hybrid. So we put a hybrid, a small printed circuit board with lots of components on, a circuit in its own right, a functional circuit in its own right, onto a printed circuit board and solder it in place. So that's basically what we're talking about. A module is a functional part of a circuit which is added to a smaller PCB, but that in turn uses the latest of technologies. If we look at surface area, this just gives you an indication of the occupied area, the surface area taken up by different passive sizes. And it's pretty obvious to us that if you go down in component size, you will obviously benefit from taking up less surface area. But you have to think also of the capability of other parts of the process. As we'll see a little bit later on, it's not just our assembly process, it's the PCB manufacturing capability that you have. So again, if you're using a supplier who can't produce track widths of less than 5/1000ths of an inch and gaps of 5/1000ths of an inch, then you're going to be struggling with this technology. So again, you're impacting potentially the cost of the PCB because you need greater accuracy to produce products. Now, something else to consider and be aware of, that over the last few years, people have been interested in the use of filletless technology. And basically what we're talking about is a solder joint which doesn't actually have a fillet anymore. So the actual pads can be smaller, or the pads can be underneath the body of the component, and we're producing what some people might say is more of a blobbier joint on the ends. And as you'll see a little bit later, one particular component manufacturer for the smallest passive component right now only has a surface to solder to underneath the component, not on the ends like the classic resistors and capacitors. But these are a couple of microsections from my own work a couple of years back, where you can see resistors and a resistor and a capacitor, and one is more like a filletless termination, the capacitor on the left-hand side, where the resistor on the right-hand side is a traditional. So the reason I mention this is that if you've got smaller pads, or the pads are all underneath the body of the component, we're starting to talk about maximizing the packaging density, which theoretically we're able to do if we don't have fillets. The disadvantage of that is the inspection using AOI, automatic optical inspection. Now, again, it depends on the machines you're using, but just like with LGA QFN packages, if a package can't look at the side terminations, then it might struggle with passive components also, where we've got filletless terminations. So it's just being aware of the capability of all of your equipment in your manufacturing facility. Now, if you look at components 0201 and 01005, suppliers have been offering small components, but really the three companies that you see more often than not highlighted as making the components readily available are Murata, Panasonic, and Rome. So if you look at 01005 and now the smaller components, these are the three component manufacturers you see and are leaders in the field. That's no disrespect to the other suppliers I've listed here. It's just that that's what I hear about, that's what I see, that's where I've been able to get components to do trials from. So obviously, when we look at components, we can look at the dimensions, and you've obviously got to look at consistency from supplier to supplier. So these are just a couple of examples with some dimensions on. So back to the terminology. So 0201 is 20 thousandths of an inch by 10 thousandths of an inch. That's the general dimension of the length and width of the package. 01005 is 10 thousandths of an inch by 5 thousandths of an inch, and as we go down inside, that's the dimension in imperial use for these parts. But you should, may I say, concentrate and look carefully at the parts. We all know as process engineers that when you look at terminations and the width of terminations and the sizes, they can vary from supplier to supplier. That's why sometimes you can't have a generic design rule for a component, because other components are slightly larger, slightly smaller, because inevitably there is tolerance in the packages. Now, when we look at packaging of the components as it's provided to you as an end user, or for assembly or for prototyping, the industry has used paper tape for many a year, and the size of that tape was 8mm. Now, when you look at the size of the components and then you look at the size of the waste on tape and cover tape, it really is ridiculous. You know, the percentage of the component to the size of the tape, you know, it's fractions of a percent as opposed to the massive amount of paper that we've got and throwing away. So the industry moved from 8mm tape to 4mm tape for these small components. And generally there also has been a change away from paper tape to plastic tape because of the tolerance requirements for a placement operation. The disadvantage to the end user is the need to buy new feeders for the 4mm tape. So it's just something, an additional expense to be aware of, but certainly the plastic tape is a lot more accurate. Also, one of the other disadvantages with paper tape that we've seen in reality with paper and plastic coverlay is static generation. And we're not talking about static generation in that damage to components can occur. We're talking about it in relationship to the components jumping out of the pockets. So if we look at, first of all, just some examples of components in tape and some of the problems that we can get, first of all, we can get missing components within the tape. Now, this is an example of when I was looking at components and just assessing the quality, the quantity, etc. And I certainly did find examples where some of the pockets were missing, i.e. there was no component in it. Now obviously a pick and place machine today will overcome that. It will register a mispick, and obviously you can look at the stats. If you look at a larger quantity, which I was doing at that time, I also found examples because of the large tolerances within paper tape. You could actually see that on some occasions the components were sitting on a different plane. So if you look here, I've just pointed out one resistor in the tape, but it's actually on its side. So when the pick and place system picks the component or draws the component out of the tape, it will inevitably place it on its side, and during reflow you might actually get it reflowed in place perfectly on its side. Again, if you look at IPC, they've got a reference to this called billboarding, so where the component is actually soldered on its side. Now if we go back to the static conversation, this is a couple of video clips that I wanted to show you just to see and demonstrate to you what can happen. So on the left hand side, what you're looking at here is the components actually jumping out of the pockets because of the static charge generated on the cover lay. So this is with the older paper tape technology. Now on the right hand side, again we're showing 4mm tape, and that's being fed and the cover tape is being peeled back, but the component is not being drawn out of it. So the suppliers supplying tape materials to the industry have improved and reduced the amount of static generated on the tape by going to a plastic tape and a plastic cover lay. They've improved the performance, the accuracy on the system. But if you are getting a lot of misplacements or mispicks, it's something again to be aware of, that static generation could be an issue to you. Now again, what I've done here is just a Bob Willis simple demonstration, and on the right hand side the video I'm showing, and I'm showing this as a loop, so it's continually looping, and I'm peeling the tape off, or the cover tape off of a paper reel, and you can actually see the charge generated as I peel the tape off. Just sort of, shows you that the video I showed you previously is in fact true. You can generate a static charge. So we've talked briefly about the 0201 and 01005 and some of the issues. If we talk and mention about the next generation. Now in the last few months, 2 or 3 months, I've been able to get some of the smaller components. Now what I show you here is the 3 different components which are being offered in the industry as the next level down from the 01005. So you notice here that first of all Rome, they're producing components, but they're using silicon technology. So rather than traditional ceramic based technology, which is used for resistor and capacitor manufacturer and is in fact used by Murata and Panasonic in these examples, Rome have gone in a slightly different direction, in that they're making the terminations directly on the bottom of the part, as opposed to the wrap round terminations you traditionally find on a resistor, so 3 sides, bottom, end and top. A capacitor, in the example of Panasonic, you've got it on all sides of the cube. You'll also notice that the Murata parts are slightly smaller than the Rome or Panasonic, so again another level down. So if we look at the components, just to give you a feel for what you would actually see if you're examining the parts, and these are parts provided to me exclusively for my own trials and tests, just to get a feel for the technology. You can see the dimensions, but I draw your attention to the right hand slide, and I'm showing the base of the Rome part. So the 2 terminations at the end, which look as though they've got little dots on, little perforations, are in fact the solder point. That's the actual termination you'd be soldering onto. And because of this type of technology they're using to produce these parts, I have to say the accuracy and consistency of these parts is second to none. And it's purely because you're using imaging technology as opposed to other technologies that have been traditionally used within the industry. You'll also notice that generally speaking, if you see demonstrations and trials conducted by pick and place companies, etc., they tend to want to use these parts because they are more repeatable than some of the other technologies. So there's no disrespect to any other suppliers, but the technique that has been used, probably more expensive, but certainly much better repeatability and accuracy if that is what you require on your circuit. In terms of the solderable terminations, the parts from Rome have got a gold finish, whereas the other parts, resistors, capacitors from Murata and Panasonic, are a traditional tin finish over a normal metallization. Again, both solder okay, not really a problem with the weldability or solderability. If we look at the packaging for the newer components in the 4mm tape, visually from the top side, as you can see on the left-hand side, you've got a cover tape in exactly the same way as any other component. If you peel the cover layer off, as you can see on top right image, you can see the component sitting in the blister. And then if you flip the tape over, you can see the molded area where the component actually sits. You're looking at the back of the tape on the bottom right-hand image. So it just gives you a feel for visually what the tape looks like. But certainly because it's plastic, it's molded, the repeatability has significantly improved from a placement point of view. Now if we look at some design rules and some pads, well first of all, you can use, and I have used, but I wouldn't recommend it, standard pad solder mask layout. So what you're looking at here in this image is copper pads with a clearance around the pad in line with the capability of your PCB manufacturer. So you have to bear in mind that as you go smaller and smaller in size, you should really allow more clearance between the solder mask and the pad. So regardless of what sort of technology that you're using, because it's all about expansion and contraction of the board and all the other processes. So if we forget about assembly for a moment and just talk about fabrication. So again, you could use individual apertures for individual pads, as I show here. I personally don't, and I suggest not using this. So for small passive components, you're not going to be running tracks underneath the component, so why have solder mask there? There is an argument with some process engineers that having mask all the way around the pad actually improves the printability. I generally have not ever seen this in the industry, not disagreeing with any of my peers in the industry, but generally when I've done it, I haven't really seen an obvious indication that it improves it. So here you've got an open aperture, as shown with a photograph, what we call a gang aperture. You can still see in this example how the pads are slightly misplaced within that gang aperture, that open aperture. Again, but that's not really a major issue. So clearances around the component would certainly be a minimum of 0.03 of an inch all the way round. And obviously, as it's an open gang aperture, then there's no resist between the pad centers. Now another option, and this is something we've included on some new test boards that we've been doing for the smaller passive components, and as you can see, I've already been doing this with 0201 and 01005 as resist defined pads. Now a solder mask defined pad or a resist defined pad is basically a bigger copper pad, and the solder mask actually goes over the copper pad to define where the solder joint will be. And this was favored by some engineers, but in terms of design, you're still using a large surface area. If you make the copper pad area bigger but don't actually utilize it to make a solder joint, you're still taking up design area. The reason this was used is by some companies to improve printing, or so they claim, also to give mechanical support. If you take some very, very small components, and you were to do push-off forces or mechanical tests on the strength of the solder joint, you'd actually find that the actual shear force was slightly higher because of the resist-defined pads. So you're actually using the resist to hold the pad onto the board. And this is done and can be done with area array components like very small BGA. So doing this in the four corners perhaps can give mechanical support without the need for adhesive on the corners or using underfill. So it's a cheaper way of giving you some advantage mechanically during drop testing or bump testing or vibration. But again, it's something you need to assess yourself. I don't really necessarily think it's a benefit on small passives, but again, I'm doing the experiments to get a feel for my own education. So these are just two examples of pads that I've used for different exercises or trials. So this was an example of a board that I produced for Cookson when we were doing initial trials on small part assembly and soldering. This is another one that I was doing on a production line for Harting, the connector manufacturer. So these are the dimensions I was using for the small parts. Again, as you do a batch of boards, you get the performance, you see what you're actually achieving, and then modify from there. Now, via in pad is not really feasible when you go down to the lowest or smallest currently available package. Via in pad can be used on 0402s, but when you start to go down even smaller, it starts to become less feasible to actually do. But if you are going to ever include vias in pads, they must be filled and ideally plated over, so it's not affecting the soldering quality. As many of you know, if you put a big hole in a pad and try and reflow solder it, you will get voids and you will get other defects, which is something to avoid. Now this is an example of actually an 0201 with vias, but the via is offset, as you can see on the left-hand side. We're making a solder connection to a larger area of the pad that's on the PCB. And then if you look at on the right-hand side, again you can see us using solder mask defined pads, so that's the blue stuff over the copper pad. So the via starts to become a bit of an issue, but it's from a fabrication point of view of the board, there is a limit. One of the other things that people have experienced is where you've got an unequal balance of the board from a design perspective of components lifting. And you know, we've been talking about this for many years, where you've got a greater volume of solder, a bigger pad on one end, or something that stops it reflowing at the same time, potentially can cause lifting and Manhattan skylining, drawbridging, crocodiling, and whatever else you want to call it. The other thing is that if you look at via in pad, when you're doing your x-rays, it can be a bit confusing. So here's an example here where we've got some voids in the bulk of the fillet around the solder joint, and what you're actually looking at is the hole in the via as opposed to a void in the solder joint. So you can see it fairly clearly on the right hand side, less clearly on the left hand side. So just be aware that some things we do might confuse us a little bit later on, and particularly it might confuse customers. They're going to be complaining about voids in solder joints when it's actually their fault because it's a design feature as opposed to a solder joint issue. Now, just to recap on lifting of components, this is just a couple of example video clips just showing the lifting of a component during the reflow soldering operation, what we call tombstoning, Manhattan skylining, drawbridging, etc. And then on the left-hand side, you can see a video clip where reflow's taken place. There is an open joint, but the component hasn't lifted, as on the right-hand side example. Now, in all honesty, I really haven't seen much evidence of this on small passive components. If we talk about 0402s, I've seen a lot of evidence of this, and it's about the design and it's about the volume of solder. A lot of people talk about other reasons, but those are the two key things. If you've got tombstoning and Manhattan skylining, it's all about the design, and then next it's all about the volume of solder. So if you can reduce the volume of solder, you'll significantly reduce the problem. If you're running in air, you're less likely to see the problem, but you're more likely to see the problem in nitrogen, because of the faster wetting and the extended movement that takes place during soldering. So just to recap and step back about the Varyum pad, what I've done here is included some dimensions of pads for the small passive components, or the smaller passive components, and actually what is required in terms of clearances when you're making a board, either for drilling or for control depth drilling, or the use of laser. And as you can see here, that basically what you actually are producing, i.e. the hole in the board, is actually bigger than the pad you need for these small components. So again, talk to your PCB manufacturer before you design in or try to design Varyum pad. Now, in terms of other potential discussion points, well, obviously, if you want to maximize the advantage of small passive components, you're trying to put the component closer and closer together, which is, understandable. But there is a limitation, and the limitation tends to be about the 100 to 120 micron. At 150 micron, you really shouldn't see a problem in terms of assembly process issues. If we talk about design direction, if you step back a couple of years ago, people were highlighting that they got more lifting of components based on the design orientation for small passive components. And I never really found this, possibly because my design rules were based on the component as opposed to general rules given to you by the supplier, that perhaps the design rules were wrong, and that's why people saw problems. Also because of the excessive paste. So orientation, really never seen that. So what I've tried to do on this slide is just give you a guideline or some feel for what I've used over the last few years, both on 0201, 01005, and what we're doing at the moment or proposing to do for the next generation. Now, I'm not saying this is perfect. I'm just saying this is my own experience. Now, I have been able to successfully assemble 0201 with thicker stencils where I've needed the thickness of the paste for other reasons. I've also used step-down stencils where appropriate, so having a 6th thou and then dropping down to a 4th thou for those small areas. More recently, I've just used a 4th thou stencil for 01005, and I'll be using a 3th thou stencil, 75 microns, both with type 4 and type 5 powder coming up in the next month to do some additional trials. Now, I don't want to use type 5 if I can avoid it, because then that's a cost penalty. Not that it's an issue to me when I'm doing trials with materials, but if you're going to be saying to somebody you must use a type 5, that is a cost penalty. So if you can achieve successful soldering of these parts on a real board with a type 4, that's an advantage. Certainly, we modify the stencils to allow round apertures, not sharp corners on square apertures on passive components. And generally speaking, we're printing 1-to-1, so there's no reduction on the pad size. In fact, we have on occasion slightly overprinted to compensate with any paste which is still held in the aperture during the printing process. Because if you look at the results you get from SPI, it's a solder paste measurement, the actual tolerance on those measurements, because of the variation in paste, is quite large. So the actual volume you might see statistically is quite significant, but you're still going to make solder joints. And I was doing these experiments only 4 weeks ago, where I looked at a board, and yes, I could see variation in the quantity of paste. I can place parts in their solder and we get joints, but the SPI tolerances that were set up were far too tight. So it was actually rejecting boards unnecessarily. So if you look at layout, we can move the solder paste deposit around on the pads as we used to, but generally speaking it's one-to-one. As I said earlier, if you've got two larger pads for your passive components, then you can get float during reflow, and that will inevitably lead potentially to shorts between terminations. So there is a limit, and as I said, that limit tends to be around the 120 micron separation, but it's also dependent on the width of the pads. So if you have too big a pad width, then obviously the components can float around. So try and balance that to get the best performance. So a couple of examples now of PCB technology problems. Now, again, when you're having boards made, inevitably there can be problems. That's one of the things that we need to understand. So what I'm showing you here is some examples of potential solder shorts due to etching on the board. So what you're looking at here is close to a short, and then on the right hand side an actual short. And this was not really to do with the etching process, it was partly to do with the imaging process prior to etching. But clearly what you can see here is a solder short which would be present if we'd processed these boards. Now, typically a board manufacturer will put boards, certainly of this technology and fine pitch technology, through automatic optical inspection. Unfortunately, these were test boards for me, and it didn't go through automatic optical inspection on this occasion. All the next batches of boards have, and hence we've eliminated the problem. But seeing problems is a benefit, because then you understand what you need to do, and also a PCB manufacturer can benefit because he can improve his process rather than rejecting products unnecessarily. Now, one of the other things that we saw during excess etching is on the left-hand side. We've got pads which literally the point at which you're putting the solder paste on is much smaller than the point in contact with the board. If you look to the right-hand side on this slide, you can see a microsection of those two pads. Now, this is a good one in that the actual foot, the bit that's in contact with the laminate, is slightly larger, but not significantly larger than the crest of the pad. So on the left-hand side image, optical image, we had a problem with printing just purely because the surface area of the pad, the top surface, is far too small. So when paste is printed onto that surface, the amount of energy pulling the paste onto the pad out of the aperture in the stencil is much less. So the problem there is the board, not the printing process. And there's just some dimensions that have been added on this microsection just to show the differences between the foot and the head of the pad. Now, misalignment of the paste deposit, we can argue that it's a printing problem, but it also can be a PCB problem. Now, when you get down to ultra small deposits and ultra small pads, you've got to consider that the board changes dimensions. And it'll also change dimensions, obviously in the fabrication process, but also in assembly. So if you take a board and do side one assembly, so print, place, and reflow, and then flip the board over, dimensionally those pads may be in a slightly different location, A, to your stencil, or to where your printer thinks those pads are. So that's no disadvantage of the printing process, it's the board fabrication. So again, that's something that needs to be considered about in the design and talking to the PCB fabricator. Also, depending on the materials used, so the laminate materials, you might get better dimensional stability of one particular material as opposed to another. So these two examples obviously show misalignment, which can be corrected. And on the second example, on the right-hand side, again, we're seeing a paste deposit slightly misaligned, but we're also seeing an example of paste which has been squashed onto the pad. So there's been paste particles on the surface, but they've been compressed. So it's probable, in this particular occasion, that paste was underneath the stencil during the print process, so contamination was present. So with smaller and smaller printing operations, again, you might need to look at increasing the frequency of under stencil wipes to improve the performance. On this example, again, of some of our boards which suffered from problems, we can actually see missing pads. And certainly on the first couple of batches of boards that we were reviewing, we did find evidence of missing pads. But again, think about the dimensions of this pad on a board. Obviously, these ones are examples where we've got no tracks associated with them, so there's nothing else to anchor them in place. You could say that if we use resist-defined pads, then you've got something to anchor it in place, which is a fine comment. But just bear in mind that we're talking about such small areas, so mechanically not ideal. But at least we've printed particles onto the laminate where we haven't done it on the pad close to it. So these are sort of just some typical examples just to be aware of when you're examining boards from your PCB manufacturer. Now, again, stepping back in time, and the reason I do this is to show you other material which is available. So during 2004, 5, 6, and 7, Smart Group ran what we refer to as the lead-free experience. And during the introduction of lead-free technology, we set up 3 production lines using convection reflow, vapor phase reflow with MPL. And I ran these features so we were demonstrating the use of the materials. So you could come along, have a play with the materials. But at that time, we also included 0201 and 01005 in the last year of the lead-free experience. And the reason I mention that is because, again, there's a lot of material which is useful in this old report of mine from 2006. Again, when you get a copy of the slides, you can download this if you want. It's about 150 pages of lead-free related stuff, but also commenting on the problems associated with small passive components as well. So what are some of the highlights or some of the problems with the original use of lead-free and lead-free soldering? Well, probably one of the most obvious things was lifting of components, but this was really only on vapor phase, and it was really only associated with the 0402 components. Didn't really see it on 0201 or 01005 parts that I processed. So again, by modifying the pads on the last year of the experience for vapor phase, I completely eliminated the problem. So again, perhaps originally the design rules weren't quite right. So we eliminated the problem. The other thing that we saw a lot of was paste exhaustion. And you'll still see this today. On some of the test boards that I was using at a feature area I was running at the NEC last month for Smart Group, we had 01005 paste deposits, and after reflow you could clearly see that in air reflow we were still getting particles not fully coalescing. And what you're seeing on the top row of photographs here are the types of joints you might see. Mechanically, they're good joints, but cosmetically, not so good. And what we're looking at is a solder joint with warts on or spots on, but the Americans tend to call it graping. So it looks like a bunch of grapes where small particles of paste haven't fully coalesced. Again, you don't get this in vapor phase reflow. You do get it or can get it because of the small deposits with air reflow on a board. So again, something to be aware of. These are just a couple of examples of X-ray. Again, perfectly good joints. There is a small amount of voiding, but they're perfectly good joints from our reflow tests and trials. A better view possibly, of flux exhaustion, which I mentioned. And on the right hand side you can see it pretty more clearly on these SEM views. We also tended to see this type of issue on other pastes which are perhaps not mainstream. During the introduction of lead-free technology, and still to this day, some other materials like tin zinc and bismuth alloys are used, which in air reflow can be problematic. The reason these materials are of interest is they're low temperature. So they're lead-free but low temperature. But again, you have to adapt your reflow process to use them successfully. And finally, on the rework and repair side, yes, you can rework these small components. I have not had experience yet of reflowing the 03005. The reason being, I haven't had enough boards to do rework on. But as soon as I've produced some successful boards, or more successful boards, I will be experimenting on this. But just to give you an indication of the size of a soldering iron tip and one of these small components, you can see the size variation between it. So what I currently use for doing 0201 or 01005, if I'm training staff on rework or demonstrating to staff on rework, I use traditional hot air tools. Now, so this is just an example of me reflowing with a hot air tool and a pair of tweezers and lifting a component off. So this is 0201. Here you see me using a pair of tweezers and picking up an 01005 out of the blister tape prior to placement. I would always use some form of microscope. You cannot do this without some sort of optical aid, or certainly I can't with my eyesight. So you certainly need good optical methods. So what I'm showing you now with this little video clip, you can see me reworking and removing a component from a pad. So basically what I've done there is I've fluxed the termination, I've preheated just with the air coming out of the hot air tool, I've reflowed it and lifted the component free. Now again, some engineers have had problems with doing this with hot air tools because they've blown the components around on the board. Now, the only reason you blow the components around on the board is because the airflow is far too high. So whenever you're buying any form of hot air tool, you must make sure you can control the feed, the air feed or the gas feed if you're using nitrogen. So very simple. Flux the termination, reflow it, and you can see me lifting the component off with a pair of tweezers. There is sometimes a challenge buying some tweezers where the tweezer points are in line. They're very easily damaged, so if you do buy a pair of tweezers that are successful and the points make contact, then try and look after them. Now this second example, this is me removing a capacitor. So here I've dropped flux onto the termination again, and I'm lifting the part off exactly like I showed you in the previous example. Personally, I don't like to use a flux pencil. I'd much rather use a needle to put a little spot of flux on the surface. And the reason I like to do this is because when I reflow one of these parts and lift it off, as you saw in the video, you can still see there's a lot of solder left. And I would suggest that if you were to just flux that again and put a brand new component on and reflow it, there would be sufficient volume of solder to make a perfectly acceptable joint. So you don't have to go and redress the pads and possibly lift the pads off as you might do with solder wick. So again, very simple, very straightforward. An alternative to that is using tweezers. Now, tweezers are available certainly for 0201 packages, and for the smaller parts you can get them from suppliers, but you need to make sure again you don't damage the tips, because if the tips are damaged they're never going to align, so you find it very difficult to remove components. So again, experiment with hot tweezers. They're great for removal of components. They are not any good, in my opinion, for replacement of the components. So you're using a different technique perhaps to remove as opposed to replace. But as I've demonstrated to you, you can use hot air for most applications. So that's just a very simple way. Now for the next component size down, different companies have come up with slightly different techniques. Now, I haven't tried this yet, but I'm looking forward to trying it out. And one of a colleague in the US at Best Technology, and also another gentleman from Metcal, what they've done is actually to get consistent volume of solder, to add solder to a joint, they've actually taken solder spheres. So as you can imagine, trying to put a blob of solder onto a pad with a soldering iron or put paste on would give you a large variation in volume, probably. And it'd be messy and time consuming. So what they actually do is put a drop of flux on the pad, and they actually put the component on, and then they put a little solder sphere on the pad. Now, as you appreciate, all of the sphere manufacturers out there do make very small spheres. So again, you've got a sphere of solder of a known volume, so at least you can control the volume of solder you're actually applying to a joint. As I said, I haven't tried it in practice. I've seen it demonstrated, seems to work, but I always like to try things out for myself. So that's just something to consider if you weren't to use just standard hot air reflow and leave the solder on the pad and then replace the part and use the solder left on the pad to create the volume you require for the joint. So most recently, with the 01005, so this is an example of some joints which were done and incorporated into the Siemens report. So just giving you sort of an overview. Here's a couple of examples of the paste deposits taken from their report. As you can see there, the volume of paste is not consistent with the size of the pad, and whether that was due to the aperture being smaller or whether it was variability on paste release, I don't know. But after reflow, they made some perfectly good joints. I would suggest that the pad width on these examples is excessive. They should be a lot narrower than you see here, personally. But again, some examples. These are example dimensions for filletless terminations. This is one of the board dimensions that I've done. And here is a reduction again, looking at reducing the sizes. And here is an example of some of the process parameters that I've used using different printers and obviously different paste materials. This is with a step-down stencil, and the placement of the components is all done manually with tweezers by myself. Now, this example shows the variability that you can get. Now, if you look at the 0201, you can see a volume variability. And if we were to measure this with SPI, laser scanning, you'd be able to detect that. If you then look at the 01005 components, again, there's a variation in the quantity of paste. So it may be perfectly good enough to get the solder joints, but obviously there is inconsistencies. So again, you're looking to improve your process all the time. Now, just to give you examples of the profiles used on some of my experiments. First of all, this is the vapor phase profile that I used on a lot of the initial work on the 0201 and 01005. This is a convection. Now, the convection process we used on a lot of the early trials for lead-free was not really what I would say the best of machines and the best of processes. As you can see here, quite a large delta T, but this was quite a complex board. So we were actually including BGA through-hole technology as well as 0201. So not ideal, as you can see from the delta T. But the result still worked. As you can see here, you've got some capacitors and you've got a resistor, and the only example of lifted components was in fact on 0402 package during some trials that I was doing, but not on the assembly process, just literally on video trials, as you've seen. So just to recap, if we look at a production line now, what we would require or what we might require for future technology. Well, first of all, I personally generally don't see the need for current technology to have to use nitrogen. But when you start to go to below 0201, 01005 and smaller, then because of the small volume of paste there, then nitrogen is a benefit. And on certainly some paste trials most recently, I just have not been able to get away with air reflow. I'd like to, because I don't want to use nitrogen unless it's necessary. But on small passive components, that's something you need to look at or investigate, or possibly use vapor phase, because that will work successfully as well. With AOI, you need to look at the capability of your AOI machine to do the small passive components and obviously other parts, but that will be a necessity in the future. So again, look at the capability of the systems. In terms of printing, you know, you've got all the major printer manufacturers out there. They can all do the technology, but the key thing quite often is the stencil, the design, and the footprint design. So it's not just the machines. The machines are there to give you the best capability, accuracy, and repeatability, but quite often even the best machines can be let down by the quality of the stencil. Now, if you can, you want to be able to still use and continue to use type 4 powder material, but consider in the future that type 5 may be necessary. But wherever I do trials, I try wherever possible to just use type 4 because of price implications. You also really need to consider either onboard inspection of paste volume or utilizing SPI for the future technology. If you're looking at placement capability, again, most of the major manufacturers have demonstrated their capability for small part processing. Again, you just want to see that demonstrated by the equipment manufacturer, but most of the well-known brands have and are demonstrating it on a regular basis. And obviously, finally, with the reflow process, it all comes down to throughput speed. So although people used to say that for lead-free you need a 6-zone oven or an 8-zone oven, for lead-free technology, it's all about throughput, generally speaking, for most high-volume manufacturers. So the length of the oven really is defined by the throughput speed you require for your production, not necessarily for the capability of the process. So just to show you a few examples of recent assembly of the smaller components, or the smallest component. So here's an example of where we've successfully printed and reflowed. You can notice some misalignment of the resist aperture in relationship to the pad. That has been improved. And here's some examples of the parts from 3 different manufacturers. So the Rome part is on the top right-hand side, where we're soldering just to the bottom termination. On the bottom left, you've got resistors, and then a capacitor on the right-hand side. So these are just a few examples of photographs that I took out of recent trials with the small parts. Again, I'm expecting to do more trials next month. This is the process we were using. We're using a deck printer, Henkel Type 4 and Type 5 paste to experiment, a 3,000 stencil. Again, all the components were manually placed by myself. And again, we'll be presenting information on the results of other trials in the not too distant future.